like to introduce our next speaker, John Evans, who will be presenting around No Packet Left Behind, minimizing packet loss in networks at scale through automated network operations. John is a principal engineer at AWS and is coming to us from UK. This is John's first time presenting at Nanog, and it's a pleasure to have him speaking with us today. Welcome to the stage, John.
Thanks, Mikhail. Yeah, thank you. Thanks, Mikhail, for the introduction. It's a pleasure to be here today. And as Mikhail said, I'm going to be talking about some of our journey that we've been on to minimize packet loss through automated network operations. This presentation is a complementary one to the one that won yesterday, which was done by Lincoln and Frederick, which looked at the infrastructure side and how we've been evolving from a network infrastructure side. And I'm going to be really focused on how we complement that from a network automation perspective. Sorry, before I get there, I just want to acknowledge my co-presenter Fabian is not able to be here today. Okay, so I think we can probably all agree that the primary job of a network is to transport packets. And if that's the primary job of a network, then the primary signal of when we're not doing our job is packet loss. But some level of packet loss is normal. We get packet loss due to TTL discards, we get packet loss due to ACL discards, but we get packet loss that is not normal, we get errored packet loss. So the problem statement that I'm going to look at today is how can we minimize that anomalous packet loss? And in doing that at scale, if we're going to minimize anything at scale, we've got to do that through automation. There was a really good presentation this morning from Jeremy, which looked at the configuration and validation side of automation. I'm going to really focus on more on the operational side of automation, and in that I'm going to set some context, and that context is 5 stages of auto remediation. So auto remediation is essentially detecting and fixing a problem that we experience in the network. And specifically the problem in this case being anomalous packet loss. So the first thing is that we need to detect and isolate the impact. So know that we've got anomalous packet loss and know where it is, which device is it occurring at. Secondly, we need to be able to identify the root cause or close enough to the root cause to be able to know what we're going to do about it, which takes us to mitigate the impact. We mitigate the impact if, for example, we had we were dropping packets due to an optical issue, which was causing layer 2 errors, then our mitigation might be to take that errored link or the errored device out of service. When we've taken it out of service, we can start to remediate and fix the underlying problem, which might be changing the optics. And then ultimately, when we've changed the optics, we might want to test whether or not it's okay and then bring it back into service. But I'm really going to focus on the first 3 parts of this problem, which is detecting the impact, identifying the cause, and then mitigating the impact. Now, before we can do any of that from an automation perspective, there are some foundations that we need. And I'm trying not to give you too many lists, but I'm going to focus on 4 different foundations. So the first one is the underlying network architecture. So if your architecture doesn't support automated operations, it's going to be hard to do the rest. The second is having accurate signal of impact, so of the unintended packet loss, which also gives us an indication of what we need to do about it. The third one is a small number of actions that we can then take in order to fix or stem the impact. And the last one is systems that allow us to do that safely. Okay, and I'm going to, start with the architecture. Lincoln and Frederick yesterday went through how we use Clo fabrics. Been used for a long time in the data center for high capacity and for scaling, but we are also leveraging that in the wide area for capacity and scaling. But Clo fabrics have other properties that lend themselves to automated operations. High degree of redundancy, high degree of parallelism, So we can take devices out of service without causing impact. Now, if we compare that to, I guess, historically how things have been done with large chassis-based routers, it makes a big difference. And it makes a big difference because we change the model from being a model where we've got, perhaps a couple of large boxes and the redundancy within the boxes, to a model where we've got very many more boxes and the redundancy is between the boxes. And that means the cost of taking a box out of service is a lot less, and we can do that without causing impact. Obviously, that means that you need to have the right control plane and data plane support in order to do that. Okay, so we started with the network architecture. I'm going to skip signals, and I'm going to go to a small number of the actions that we take. And the reason that I'm going to go to the actions that we take is because we need to work backwards from those actions to work out what signals that we need to know what we're going to do. So operationally, there's only a relatively small number of actions that we can take in order to stem unintended packet loss. We can take a device or a link or a set of links and devices out of service. We can put a device or a link or set of devices and links back into service. We can roll back an ongoing change. We can move traffic, or we can escalate to an operator, and we want to, as far as possible, not do the last one. But to know which action we need to take, we need very precise signal. So an example of where that matters is if, for example, we've got congestion and we detect packet loss. If we were to take a device out of service where we're experiencing congestion, we're going to make that problem worse or shift that problem somewhere else. So, it's a clear case where if we know it's congestion, we know that the solution is not to take a device out of service. Whereas if we know that we're dropping packets due to errors, then we would take a device out of service. Okay, so given that relatively small number of actions, we need signals that are going to map to those actions. So then to the question of how do we get those packet loss signals? Now we need to satisfy a few or meet a few requirements. So we need it to be accurate, and accurate to the point where we can detect low-level anomalies. We need to have enough information, enough context to be able to know what action to take. So we need to know which device, we need to know what the underlying cause is. And we need to do that at scale. And doing it at scale means that certain options, certain things that you might be able to do are probably not applicable. So if we consider different methods of measuring packet loss, there are 4 underlying features that really give us the information to tell us, whether or not that packet loss is anomalous and what action we should take. So magnitude, the first one, how many packets are we dropping? What percentage is it of the total? The location, the specific device or link where the problem is happening. The cause, and the duration, how long it lasts for. I put context in brackets there, and I'm going to touch on that later on. But let's focus on 4 primary features of packet loss signal, from which, from those features, if we've got sufficient information, we could determine what action we're going to take. Now, there are 2 primary methods that we've got for measuring packet loss. Active monitoring, we're putting synthetic traffic on the network and seeing what happens, or passive monitoring, we're extracting data from devices about what's going on. So let's consider active monitoring in the context of those 4 features. So firstly, magnitude, and the magnitude of the loss. Now, active monitoring is putting packets on the network, so it's sampling what's happening, and I'm going to talk about that in a bit more detail, but the fact that it's sampling limits the accuracy of the measurement of active monitoring. So it's good to a level, but there's a level below which you'll lose visibility. In terms of location, if you deploy a mesh of active monitoring probes and you do triangulation of the loss between that mesh, it's possible to determine the location of packet loss and to pin that down to individual devices. But it requires that you do that kind of analysis. We get duration, but we don't get cause. it's very hard to determine through active monitoring what the underlying cause of packet loss is. So I'm going to focus a little bit on that first point, which is around the magnitude and the issues there. And the issues stem really because with active monitoring, we are sampling in time and in space. So firstly, let's consider sampling in space. So we focused on using a Clo fabric. We got an example here. So in a very simple example, if we've got a 3-tier fabric, we've got 4 links from the host to tier 1, 32 links tier 1 to tier 2, 8 links from tier 2 to tier 3. From one host to another host, we've got over 1 million possible combinations of link paths through that single fabric on its own. Now, in our network, we have any end-to-end path goes through multiple fabrics. And so we've done the calculation here of how many link path combinations you end up with end-to-end. And you can see it ends up being a really big number. So it's not possible end-to-end to monitor every single end-to-end path with active monitoring. You've got to sample in some way. And typically you'll optimize for something like trying to make sure that you've got coverage of at least each link with a minimum number of probes. How many probes on a link matters. So if we have, let's imagine we've got a 100 gig link, 10 million packets per second, and we've got 1 active monitoring probe per second, and we drop a probe, we don't actually know what rate we're dropping at, whether it's 100% or whether it's 1 in 10 million. It's going to be somewhere between the two, but we don't know where between the two. And that's purely a function of sampling. Now, in practice, we're going to put more probes than that over a link, but we're not going to put 10 million packets per second over a link. So our accuracy is going to be limited by the probing rate. And that's what this chart shows. So this chart shows the blue shading shows the reported packet loss with active monitoring, and the orange line shows the corresponding reported packet loss with passive monitoring. With passive monitoring, we're not sampling, and you can see the maximum reported packet loss we see here with passive monitoring is around 0.5%. In comparison with active monitoring, it's in about the sort of 4.5%. It's up to about 5%. So the difference is 4.5%. And that's a function of the active monitoring probing rate that you have, but you're always going to have that difference because you are sampling. Okay, so we had our 4 features that we were trying to satisfy. We've met 2.5 of them. So let's consider now, our only other option is passive monitoring. So let's consider passive monitoring as an alternative. So with passive monitoring, it's unsampled in time and space. So in theory, in terms of measuring magnitude, loss magnitude and accuracy, it should be really good. In practice, what we see is that actually the passive monitoring loss reporting varies quite widely by platform. And so it's as accurate as your loss reporting is. We get location because it directly indicates a reporting device. We don't have to do anything algorithmic to triangulate, and we know where the loss is happening. We get duration, but we don't get cause. And we don't get cause because the packet loss reporting doesn't really, the classification doesn't really align to cause and the actions that we want to take. But with passive monitoring, we've got the option of potentially fixing these problems. So we can look at magnitude and we can look at cause and we can see what we can do about those problems. So let's focus in on passive monitoring and focus in on how it's defined today. There are 2 metrics, if we look at the standards, there are 2 metrics that are pretty much supported across all platforms, IF in and IF out discards and IF in and IF out errors. Originally defined in 1991, 32 years ago, and I think it shows. So clearly networks were a lot smaller, automation of networks wasn't a thing. So if we look at IF in discards, the number of inbound packets which are chosen to be discarded, one possible reason for discarding such a packet could be to free up buffer space. Okay, so it could be, it doesn't say it is, and it doesn't list the other reasons that could be included here. So is an ACL discard, should it be included in IF in discards? it's totally open to interpretation, and it has been open to interpretation. If we look at IFIN errors, the number of inbound packets that contained errors preventing them from being deliverable to a higher level protocol. There's a key word missing here, which is, it doesn't say discarded packets. So in some cases, this can account for errors where you've thrown a packet away. In other cases, this can account for errors where you haven't. So again, significantly open to interpretation. And I think, to set some context, the number one in the American music charts in 1991 was Bryan Adams. I've included that for one of our Canadian colleagues who's here. And I think we've moved on musically since 1991. I'd like to think we have. But I don't think we've really moved on in terms of discards. So we've looked across, I guess, a set of implementations. Whilst you get more discard reporting than those two metrics, it's inconsistently implemented. So there's a number of things that we've seen looking at different implementations. So one is not reporting all discards, and so that can appear like a grey failure. The box knows the discard's happening, but it's not exported, and so you don't know about it. Another is duplication of discard metrics. So if you're reporting the same discard in two different classes, how do you know what the underlying issue is? We've seen the same OID, so the same, notionally the same metric, meaning two different things across two different platforms, which means that you have to know the platform context in order to understand, specifically what's going on. The case of IFIN errors I mentioned, and lastly, where the discards are reported and what they mean, it changes. So in some cases it can represent, in some cases it be assigned to an interface. In other cases, it can be assigned to the box. In other cases, it can be some context in between, maybe part of the forwarding pipeline. And the reason that we've got this inconsistency is because there are no clearly defined semantics for packet loss reporting. So we've tried to fix, or for our networks, we've tried to fix that. And so what we did was we worked backwards from the actions that we were trying to take. So understanding that, ultimately what we want to do is take one of those actions in network operations. Let's start with the actions and then work backwards to what do we need from the signals in order to be able to clearly know which actions to take. So we defined a classification scheme, we defined a set of discard semantics around that, and then across a set of platforms, we looked at the underlying hardware counters, which can vary depends upon the platform, but 32 up to 256 different underlying counters. And I don't mean in terms of interfaces, I mean underlying reasons why packets may be dropped, which could then be multiplied by interfaces. And we mapped them to the classification scheme. I'm going to take you through the classification scheme and then take you through what our experience was of doing that. But in order to define the classification scheme, we worked backwards from the actions that we wanted to take, but we also need an understanding of where and why packets get dropped. So this is an example, I guess a generalized example of a forwarding pipeline in a single ASIC device, and we've got packets coming in at the left and packets going out at the right. So if we work left to right, the first thing that we've got is that we can drop packets on receipt due to layer 2 errors in the received packet. So we may have some form of layer corruption or some form of invalid packet at layer 2. If we're okay at layer 2, then we get to the layer 3 forwarding pipeline, and we might intentionally drop packets due to ACLs, due to polices, or due to configured null routes. But then we may have a set of reasons why we unintentionally drop packets. We could have no route to forward the packet to the destination. The TTL could have expired, or we might have errors in the L3 packet, or other errors that don't fit those other criteria associated with the box not being able to forward the packet. We might have, for example, a parity error in hardware. Once we get through the ingress pipeline, then got a shared buffer, so we could have a no buffer drop if we have got enough buffer to queue the packet. And then on egress, we can also have reasons that we drop a packet, intentional reasons, ACLs, polices, and then also the potential for errors also on egress. So given that, we can then define our classification scheme. We've defined it as a tree. At the top of the tree, we've got all possible packet discards. And the first branch of the tree is to differentiate between things we intend to discard from those things that we don't intend to discard. So intended discards, ACL, police, and null root. The other branch of the tree, then, those things that generally we don't intend to happen, or we don't intend to happen to some degree, and I'll touch on the degree. So this could be no root discards, no buffer discards, TTLSC discards, and errors. And a number of these classes, then, we can have subclasses for. So no buffer discards, if we're doing QoS, we want to know which queue we're discarding from. If we've got errors, so receive errors, we may want to know whether that's a layer 2, layer 3. If it's layer 3, we may then want to subdivide into what the underlying cause was. And then, given that classification, we need a set of semantics in which to implement that classification. And the simple version is report all packet drops, report them once and only once, no duplication, report them where they occur, preferably at the interface, and report them in the right class. And that's simply put, that's it. There is a longer version that you'll find in an IETF draft that we've written on this. So we did that. We did that across a set of hardware platforms. And here's some feedback on our implementation experience of having done that. So the first point is that the number of discard classes is a compromise. So if we consider a platform that has 255 drop reasons for dropping a packet, exposing 255 in most cases is just overkill. It gives too much information and slows down resolving a problem rather than speeding it up. So we need to abstract that to some degree. So we need enough granularity to be able to take the right action, but not that much that it's going to slow things down. Also, at scale, if you're reporting discard classes per interface, and you've got a lot of interfaces, the more discard classes you add, the more your data grows. So there is a sort of a data volume to take into account as well. Secondly, null root versus no root discards. So a null root, say I configure a null root to intentionally drop certain traffic. But let's say I receive a packet that for which I have no destination. In that first case, I've intended to drop the packet, so I'm not going to take any operational action. In the second case, that might be an issue, might indicate an issue. But a common way of implementing dropping packets when you haven't got a root is to implement a default null root, okay, in the box. That's what's sitting there, and that's what ends up dropping the packet. So in that case, it can be hard to differentiate between a no root discard, which you want to know about, and a null root discard, which you don't. There are ways, to work around that, but they add some complexity. Similarly, we end up with some ambiguity. We can end up with some ambiguity on access lists. So we have access lists for packets going through the box, and we have access lists for packets going to the CPU to protect the CPU. You really want to be able to differentiate between those two. But again, in some cases, if it's the same ACL or the same type of ACL that's being applied to implement both, it can be hard to separate between them. And so you may not be able to differentiate between a transit ACL drop, which will take no action for, and a 2 CPU ACL drop, which you might take an action for. The 2 CPU ACLs cause another issue, which is that it's common on most platforms to report the number of TTL exceeded packets that the CPU has responded to with an ICMP TTL expired. However, it's also common to have a policer on the path to the CPU. So that means you're only responding to a subset of the TTL packets that you're actually dropping. So what you really want is to know the number of packets you've received with a TTL of 1 that you are going to drop, not the number that you process by the CPU. Okay. So again, there are ways to do that, but you need a different counter to be able to do that, to count TTL. TTL is 1 on ingress. The last point is that you can't detect all issues with device level classification. And a common question I've been asked is, how can we determine if ACL discards are intended or due to an incorrect ACL? And the answer is you can't, just due to the metrics on the box. You need some other context. So for example, if you know that the number of ACL discards has significantly changed from before a change to significantly different before a change to after a change, then that may give you the information you need. But just the discard stats on their own aren't enough. You need to know that a change has happened, when that's happened, and that there's a difference between them. So you can't tell everything just from having the right discard classification. Okay, so I realize it's been a lot of text. We're gonna get exciting now with a little video. So what we tried to do here is to actually visualize packet loss in action. And we're using a tree map. So to explain the tree map, what we've got is 4 boxes here, and the boxes represent a device in the network. And within those boxes, there are both the packets transmitted and the packets being dropped. The packets transmitted is the white section. The packets being dropped are then colored according to the legend on the right-hand side. And as a video, each frame represents 30 seconds in time. So we're looking at a sort of time slices through what's happening in the network. And so if I start the video, what we're going to see is a small number of null root and TTL discards, and then a sudden burst of receive errors, and then having detected those receive errors, we remediate the issue and they go away. I should point out that we've normalized the underlying loss rates here by using a log2. So that makes the small things look bigger than they are, but it's so that you can see everything. But essentially you can see that you're able to visually see that an issue has happened. In this case, you're able to visually see that it's a receive error across all devices, in this case in a layer. And this is indicative of an upstream optical issue that then impacted all of the an issue with the upstream device that impacted all of the downstream devices. Okay, is that exciting? Okay, we'll try again. So second example, this one, and this one actually is, we've got 20 devices here. This is actually spread across 2 layers. I'm not going to do any talking. I'm just going to play it. This one, I think the title probably gives away what it is. But you see, as we start off, you see a similar background, low level of loss, null root and TTL discards. And then the anticipation was worth it, wasn't it? We get a burst of TTL discards, much higher level of TTL discards. In this case, that was due to a short duration routing loop, where again we were able to detect it. You can see that if visually from this we can understand what's going on, I can understand that I've got a transient routing loop across a layer. We're able to programmatically also identify what's going on, and so. So by referring back to our 4 features that we were talking about earlier on, the magnitude of loss, the location of loss, the duration of loss, and the cause, we can map those to the actions that we would take. So in the case of the receive errors, the action would be to take the upstream link or the upstream device out of service. So we focused in on passive monitoring, and we had an issue with magnitude, we had an issue with cause, but if we actually address the underlying implementation, the classification scheme we use, the semantics, we can actually fix those 2 issues so that we can address all of the features that we need to take to minimize packet loss in an automated way. The last thing that we need is systems that enable us to take those actions safely. So we don't just take those actions without regard to the consequences those actions might have. And so at a high level, trying to understand what those systems look like. We have pervasive active monitoring with triangulation and detection of impact. In parallel then, as we've discussed, pervasive passive monitoring with anomaly detection to be able to identify anomalous loss. The outputs of those go into a system to deal with correlation and root cause analysis to actually be able to work out from those inputs what actions should we take. There may be other inputs, other event data that's an input to that system. But then before we take an action, so that determines what action might be taken, but before we take that action, we need to consider the risk of taking that action. So is it safe to take this device out of service, or have I not got enough capacity? And if I take that device out of service, might I actually make the problem worse? So it's really important not to, have that as a component of the system to ensure that the automated actions that you take don't actually degrade the performance of the network. That is pretty much everything that I had, but I guess to summarize, I'll focus on a couple of points. The one is that in order to automate operations in the network, you need the underlying foundations in your network to do that. So the right architecture, the right signals. And in terms of signals, you need precise signals to be able to take those actions. Trying to take actions deterministically from low quality data isn't very successful. We've written an IETF draft on that, and if you have a shared interest in this area, we'd be very interested in feedback or collaboration. That was everything I had. Thank you. Any questions?
Adair Thaxton, Internet 2, we're the best. What does that sort of monitoring look like at Amazon's scale? And how long did it take you guys to put it in production and get it to be a trusted tool?
Good question, and I think there's probably multiple parts to that. So, one is the device level signal. Then there's the collection of that, the processing of that, the actions. And we haven't done that all in one piece. We've got multiple pieces. If I consider the last piece, which is or if you consider the signal piece, which is the packet loss reporting, because if you haven't got that piece, the rest is harder. And in most cases, people have pieces of those other systems, if not all of them. It's probably taken us 18 months in order to be able to work through that problem space. But I think part of the point of the presentation today was, the definitions really, considering the job of a network is to transport packets, that's why we're all here. The primary signal when we're not doing a job is when we're dropping packets, and the current state of the definition of that in the standards is really poor. So I think if we can, as a community, improve that, agree on what that should be, and then any vendors out there know what they're implementing to and why, then hopefully you won't have to spend 18 months doing that. Thanks.
Right. Hi, Alex Bortok, Ixia. So on the question of active monitoring and specifically the triangulation part of it. So I wonder if any best practices you can share, for example, things around like is it important to make the path deterministic through the fabric, or maybe you use in-band telemetry, any of those things that actually make triangulation work for you?
Yeah. So so good question. So you need to know, to be able to do triangulation, you need to know your topology. Various ways that you can get the topology. If you know the topology, if you prescriptively know the topology, that's great. Trace routes are a method. The IGP carries a view of topology. But yeah, you need some view of topology, and you need to understand how your probes or your agents fit to that topology in order to be able to do it. I think there are several papers that cover this, NetNORAD, and others in that vein, which talk about the algorithmic approach for doing that.
All right, thank you.
Thank you.
Here, Marcos Sanz from DECIX. very valuable effort what you're doing, and I love the animation in the slides very much.
you.
Now,
Thank Fabian for that. He did that.
That was very visualizing, and I quickly skimmed through the draft, and I couldn't find any wording on the following. So my question is, do you think it is possible that one packet gets discarded for more than one reason?
Yeah. Okay, good question. Good question. Yeah, sorry, have you finished?
Yeah, because I mean, even when things go wrong, then sometimes many things go wrong at the same time. So I think it's not that, yeah.
Yeah, it's a good question. And to some extent, that depends upon the platform. So depending upon the way in which the platform is built and the order in which those things are done, you know, one platform may report it one way, one platform may report another. I think I wouldn't want to be prescriptive about how a hardware vendor goes and builds their pipeline. But what we should know is the ordering in which that's done. So if it is possible that you may have something that is hitting that is going to hit multiple possible drop, you want to know what's coming first. So you want to know if I'm seeing this, it means I'm not seeing something else.
That's correct. But there is one thing you maybe should be prescriptive about, and this is one of your goals. You don't want something to be counted more than once, because maybe some errors in your diagram, you went from left to right, and there are different layers, and maybe some of those errors are detected on the same step, and maybe some vendor decides to go up with some counters at the same time. So I think there should be some prohibition. Don't do that.
Yeah, I think that's good feedback, and thank you. Yeah, and if you want to send me an email, happy.
I try to find some wording for that. Thank you.
Okay, super. Thank you very much. Any more? No? Okay, well, thank you very much. Thank you for your attention.